Hi everyone and welcome to this new video. In this video we continue the Active Directory Exploitation series, and specifically the focus for this video will be the Kerberos protocol. In this video we will read all Kerberos components, we will analyze all Kerberos messages, and we will use a pickup trace that was recorded in the local testbed, in the Active Directory testbed that I showcase how to set up in the first episodes of the series. As always, the idea is to give you a lot of intuition and a lot of details so that you can understand deeply these ideas. If you find the video useful and interesting, support the Xstamp project by subscribing to the YouTube channel and sharing this video with like-minded people to help me grow. Thank you very much and enjoy the video. So let's do a little recap on what Kerberos is and what is the role that it plays in the context of Active Directory. Kerberos is an authentication key agreement protocol. This means that Kerberos allows two entities to establish a shared secret key securely, starting from an insecure communication channel. So these are the first ideas that I want you to understand. We are in the context of a network. This network is made up of many components, and this network could be insecure. Insecure in this case means that in the channels that form this network, there could be eavesdropper. There could be people who manipulate the traffic, like maybe in this link, there's some eavesdropper and he's trying to act maliciously, so he wants to steal the key. Okay, so that's the idea. So Kerberos is used to share a secret key. Now, why do you want to share a secret key? Well, that has to do with modern encryption. How does modern encryption works? Essentially, there are two big schemes of modern encryption, which is public key cryptography and symmetric key cryptography. So in the symmetric key cryptography, the idea is that you have a shared secret key, which is the same for both parties, and you use that key to protect the messages in the communication. So for example, to protect the confidentiality of the message by encrypting the message so that no one is able to see the message. So that's one thing, that's confidentiality protection through encryption. Another thing is how do we protect the integrity of the message? Well, there are cryptographic schemes that use a shared secret key that allow you to protect the integrity of the message by signing the message with message authentication schemes. So all of these work with a shared secret key. Of course, the problem is how do you bootstrap this secure communication if you don't have this shared secret key? And that's where Kerberos comes in. Now, Kerberos allows two entities of the network to establish a shared secret key in an insecure communication channel. Now, this is also what happens in the web, right? But in the web, we do not have Kerberos. This is an important point. In the web, Kerberos is not there. Instead, we have HTTPS. And HTTPS is built on top of TLS. So the stack is HTTP, then I have TLS, and I have TCP, and then I have EP. And then I have all the protocols. So this is the protocol stack for securing the web. And this works actually by using digital certificates, X509 digital certificates, to authenticate entities and a lot of other cryptography. So the idea is that TLS uses a different cryptographic scheme, which is the public key cryptography. So Kerberos is a symmetric key cryptography. TLS uses both symmetric key and also public key. And the big difference is that in the TLS world, in the web world, we have the only authority we trust are the so-called certificate authorities to authenticate the digital certificates, which means that to authenticate the server, you use this concept of digital certificate, which is handled by certificate authorities, which are called CAs. But in the communication themselves, there are just two parties communicating. So there is the client and there is the server, and they exchange certificates and stuff like that. But at the end of the day, in the communication itself, we just have the browser and we just have the server, and they communicate and they establish a secure channel like this. Now, the difference between the web and Active Directory is that in the web we have TLS with digital certificates. In Active Directory we have Kerberos, and in Kerberos entities are not authenticated by digital certificates. Kerberos is based only on symmetric key cryptography, and instead entities rely on a centralized server. So this is a really key point to understand, a really key difference to understand, is that for Kerberos to work, we need a centralized point of trust, which is known as the KDC, the Key Distribution Center. And this KDC knows long-term secrets for each entity involved in the communication. So the idea is that when a client wants to communicate with a service, for example, an SMB service, an LDAP service, whatever kind of service in the context of Active Directory, they can establish the secure channel, so they can share a key, but to share this key, the client will have to communicate with the KDC multiple times, so there's gonna be multiple messages with the KDC to generate tickets, and these tickets will be encrypted using a bunch of different keys. So the idea is that this system can work only if we have this central point of trust, which is the KDC, and the KDC has to know long-term secrets for the client and for the service. So if you compromise the KDC, the entire system is compromised. If the KDC is safe, then the system can give you these security benefits, can allow you to establish secure communication channels in an insecure network. And so basically by using such knowledge, so the KDC, by using the knowledge of these long-term secrets for each entity, it is possible to establish ephemeral session keys that allow clients to authenticate to services. So here with the word ephemeral means a key that is only used for protecting that particular session, and that as soon as that session is over, the key is destroyed. The key no longer works, the key is no longer useful. So basically that's the idea. Now, when you build a cryptographic scheme, you can always rely on an already existing implementation, on an already existing idea, essentially. And Kerberos specifically, it is built on top of the Needham-Schroeder symmetric key protocol. And in the references of this video, you will be able to find various links, such as the Wikipedia description of the Needham-Schroeder protocol that describes the key exchange that happens within Kerberos. Then you can find the official RFC, which defines the Kerberos protocol version 5, so the Kerberos Network Authentication Service. And in this document, essentially, you will find all the details of the protocol. It is very long, it is very dense, but it is very useful if you have a specific doubt. Always check the RFC. And then here I also put the Kerberos v5 Unix user guide. So this is a specific implementation of Kerberos, and once again, it's another way to describe how it works. And in this case, you also have like practical setup on how to set it up, essentially. So that's basically the idea. So in terms of this video, in terms of what I want to essentially explain about Kerberos, we will see two different things. First, I will describe the components that make up Kerberos, so different key players involved in Kerberos, and then I will describe the full sequence of messages that are sent between the client, the KDC, the client, the service, to properly authenticate. And to help myself here, I have a pickup dump that I'm reading with Wireshark, so that we can analyze in detail each field of the protocol, the meaning, and things of the sort. So this is just to build a good understanding of how it works. In future videos, we will see how to actually attack it. So of course, we start with the Key Distribution Center, the KDC. Now the KDC is the core component of Kerberos, and it deals with initial authentication and with the issuing of tickets. It is made up of two specific services, the authentication server and the ticket granting server. Now each of these two services generates specific tickets, so that the way that the authentication is carried on is through tickets, and tickets will be encrypted with specific keys. So the authentication server, its job is verifying the user identity, so verifying that the authentication request was properly authenticated. So like, okay, you are trying to authenticate, did you put the right password in the context of this message? And when it does so, if authentication succeeds, so like if everything is fine, the user knows the correct password, then it generates a ticket granting ticket. Now, when you have a TGT, you can exchange the TGT to obtain a so-called service ticket. So either you can call it service ticket, or you can also call it ticket granting service. So TGS is the same thing. However, with TGS, we also mean the second server in the context of the KDC, which is ticket granting server. So that's the idea. Now, the authentication server, as I said, authenticates the user and generates the TGT. The ticket granting server instead uses the TGT generated by the authentication server to generate the service tickets, the one that you actually use to authenticate to services and to use those services. So this can be already confusing, I understand. Just imagine this protocol split up in different phases. In the first phase, we find authentication in the context of Kerberos, so authentication with KDC. And once this is done, you will have a TGT. So all the entities that have a valid TGT are currently authenticated in the Kerberos context. This does not mean, though, that you have access to services. If you want to access a specific service, you need to trade, you need to exchange the TGT, you need to use the TGT to obtain a ticket for a specific service. Ticket for specific service. Assuming that you are allowed to do, of course, service. And this ticket for specific service, we can call it a service ticket, ST, to not confuse. So once you have this service ticket, then you can actually use ST and authenticate to service. So the first authentication happens within Kerberos. The second authentication happens within the actual service itself. And of course, in the second step, the ticket granting server has to check if your TGT is valid or not. So there's actually also a second authentication in this middle context to actually generate the proper service ticket, essentially. And the service ticket is what you actually use to access the resources you are interested in. Now let's try to build intuition on this. Why are we splitting this into two steps? Why couldn't it be that I give the password to the authentication server and he gives me already the service tickets? It's like, why it cannot work like that? And here the basic intuition is that once you have a TGT, you can use the TGT without inserting your password every time, without putting information related to your password in the messages, in the request messages. So you can use a TGT to issue many service tickets, service ticket 1, service ticket 2, service tickets 3, like even 100. And as long as the TGT is valid, you will get all those service tickets. Now, if we remove this step instead, every time we ask a service tickets, we would need to send information related to the user long-term password, which is not good. So we want to avoid that. We want to avoid the exposure of such secrets. So a more like a scalable way of doing this is by splitting it into two tickets. One abstract ticket that allows you to obtain the more specific tickets. And so this is the KDC, the Key Distribution Center, made up of two specific services, authentication server and ticket granting server. Then we find the concept of realm. Now, a Kerberos realm defines a logical security boundary that contains a group of principals. Now, principals can be users, services, computers. Principals can be anything that can be authenticated with Kerberos. We will talk about principal later on. So like a realm is just a group of principal. And this group of principal trusts a specific key distribution center for authentication purposes. So it means that this realm uses this specific domain controllers, which also define a KDC. Of course, if you have multiple domain controllers in the same domain, they will have like replicated and shared data, but essentially we're talking about one logical KDC. And so within a single realm, there is a single key distribution center. So in Active Directory, a realm is automatically created when a domain is initialized. And the Kerberos realm is the uppercase version of the Active Directory domain name. For example, to discover the realm your user is currently execute the following command, which print the user principal name, UPN. So you say whoami/UPN. And if you want to try this out, so we say whoami/UPN, user principal name. So we say whoami/UPN, and we get leo@exam.lab. Now this thing is the realm. Now in this case it is not uppercase, but essentially the realm is this thing uppercase. So you can also get this using the klist command, which lists out all the current Kerberos tickets active in your session, essentially. So look at this, we have @exam.lab. This time it is in uppercase. And notice that here we have 2 tickets, not 1. Why? Because the first ticket is a ticket granting tickets, so it is called a TGT. And we can see that because the server it is based on, it is the KRB TGT. So it is the Kerberos KDC. So essentially, this defines this ticket as a TGT, as a ticket granting tickets. Here we find the start time, the end time, the renew time, the session time, whatever, the way that the KDC is called, which is DC01. And then we have a different tickets. This time the server is not anymore KRB TGT, but it is LDAP. So this second is actually a service ticket. So this one is a service ticket that was obtained with that TGT. And this service ticket is used to connect with LDAP, so with the LDAP server of the Active Directory domain. So that's the idea. So here we have, of course, how the ticket is encrypted, a lot of information, we will analyze it later on, but that's basically the idea. We have 2 tickets because we have a TGT and we have a service ticket too. And so basically, yeah, for example, for the domain exam.lab, that Kerberos realm will be exam.lab in uppercase. So Kerberos realms are related to the domain, to the name of the Active Directory domain. So that's the thing for realm. So like realm is just a grouping of principals. Then what is a Kerberos principal? Well, a Kerberos principal is a unique identity to which Kerberos can assign tickets. So it is an identity that is considered in the context of Kerberos. Now there are different types of principals. User principal, so they represent individual users in the context of in a context of a Kerberos realm, and this is also known as a user principal name, so UPN. So when we executed the command whoami/UPN, this one is the Kerberos principal for the user Leo. So this is what identifies us. It is like our surname, our email in the context of Kerberos. It is our identifier. Then we have the service principal. So it represents a service that requires authentication and authorization to be accessed by its clients, like an SMB server, an SQL, an HTTP, and also an LDAP server. Why not? And indeed, in this example, in this practical example, this is the service principal for LDAP. So notice that they have this common pattern, some text here, then the symbol @ and then the name of the Kerberos realm. So services need to register proper service principal names, SPNs within Active Directory. Once this registration has taken place, Kerberos can issue tickets for the registered services to be able to use that service. So if you want a service ticket for a specific service, say service 1, this service needs to be registered, needs to have a proper service principal name. If it doesn't have an SPN, then you cannot get a ticket through Kerberos. And then we have the host principal, which represents computers in the context of a Kerberos realm. Now, each principal has an associated secret key. So this is a long-term secret key. It means that it does not expire in one session, but it lives through many different sessions. And this is used during the key agreement protocol to provide authentication. Because we said that Kerberos is used for authenticating and for exchanging a secret key in an authentication-based way. How do we do that? Well, it is because the KDC knows for each principal, so for each user principal, for each service principal, and for each host principal, the KDC knows the related secret key. And by using this knowledge, the KDC is able to establish this secure channel. So the single entities, they only know their key, right? So if I am a client here, I'm a client, there's a server, there's a KDC. The client only knows his key. The service only knows his key. By communicating with the KDC, they are able to essentially establish a shared key among them. So that's basically the idea. So principal follows a common name structure, which is primary/instance at realm. So the primary identifies the entity. The instance further qualifies the primary, so with extra stuff, and then we have the realm, which defines the Kerberos domain in which the authentication has to take place. So if you change the realm, you're also changing the KDC, you're changing this underlying database that associates principal to secret keys, and therefore the key agreement will not work out. So here a bunch of commands. So the previous one, whoami/upn, klist to list out all the tickets in your current thing. If you want to list out all the service principal names registered for DC01, you can do set spn-al dc01-l dc01. So this command, you do this command. Okay, no, I copied wrong. This command and look at this. So we have all these service principal names, and we also find the LDAP, of course, which is what we saw here. So we saw LDAP dc01.examp.lab. So it's this one essentially, LDAP dc01examp.lab/exam.lab. So this is the service principal name, and then we have the exam.lab, so the realm. For example, we can also register a new service principal name for the username Leo. So we are associating a new service to this particular user, which by the way is gonna be dangerous, and we will see a specific attack on this later on, not in this video, but in a future video. And if we do set spn-l, so for this user, so for example for the user Leo, here you can see, for example, look, we have an http web server.exam.lab. So we have this particular service principal name. And this exposes this account to a specific attack called Kerberos roasting, which, as I said, I'll show in later videos. So far we have the KDC, which is this centralized component that holds all the secret key of the various entities. We have the concept of realm, which is just a set of principal. And then we have the concept of principal, which is the single entity that can be authenticated with Kerberos, so that Kerberos recognizes as something. It could either be a user, a host, or a service. And for each entity, for each principal, Kerberos has an associated long-term secret key within the KDC. So that's the idea. Now, to finish off the components, we need to talk about the two types of tickets in the context of Kerberos, which is the ticket granting ticket and the service ticket. So, a ticket granting ticket, TGT, is a Kerberos ticket that is used to issue service tickets through a key distribution center. In secure deployments of Kerberos, this ticket, the TGT, is issued only after proper authentication with the authentication server AES. If authentication is successful, the KDC will issue a TGT. If the TGT is issued prior to proper authentication, we have an attack called AS-REQ roasting that can be performed on the Kerberos realm, and we will see in practice what this means and how to perform it in a future video. So, this video is to build understanding on Kerberos, and then we will see how to properly attack it. Now, the TGT will contain various information such as the user ID, the TGS ID, so this is the ID of the server who will receive this TGT, expiration time, this called TGS session key, which is also sent to the client but in a different message, so that the client also knows this session key and can use the session key to prove its authenticity, so to prove the authentication, a bunch of ticket flags, so a lot of information. Notice that the TGT is not sent in clear. Now, this is an important point. The TGT is not just sent as it is encrypted, and it is encrypted with the KDC secret key. Why? This is used for authentication purposes. We will analyze it in the flow, in the message flow. So this is an example of a TGT, as you can see here, Kerberos TGT. as we saw before. So notice the information. For example, we have the user principal name, UPN client, the service principal name, which is the name of the TGS, which is also the KDC. There is an initial flag here that specifies that this is the first ticket. There is the pre-authent flag that specifies that authentication occurred to obtain the ticket. So this is important. And then there is the encryption methods to protect the ticket and things of the sort. So here is protect. So this is a simple example. So this is the ticket granting ticket, and then we have the service ticket. So a service ticket, which is also known as ticket granting service, I mean, Kerberos is really confusing with all these terms, but the idea is that this is the second ticket, right? And this ticket allows an authenticated user, which means a user authenticated to the Kerberos realm within the context of Kerberos. It allows this user to access a specific service or resource by using a previously obtained TGT. So it is issued by the KDC and specifically by the ticket granting server. Because remember, we have two tickets, which means that the KDC is split into two different roles. Into the authentication service AS, which issues TGT, ticket granting tickets, and into the ticket granting server, which issue server tickets, also, or TGS, ticket granting service. Like, super confusing all these terms, but the idea is that the KDC has two roles. Authentication role for the ticket granting ticket, and the generation of the service tickets role through the ticket granting service server, essentially. So once you obtain a service ticket, you can present it to the target service. The ticket is created in such a way so that only the service can decrypt it with its own secret key, and it is used to validate the identity of the user, the request of the user, and things of the sort. If the service ticket is valid, the user will be allowed to access the resource without entering passwords. Because the idea is that at the end of this, once the service ticket has been sent to the service, client and service will have a shared session key for that particular session, and they will be able to essentially interact with each other. And this is another example of a service ticket, once again, authentication with the LDAP server. So in this case, the service principal name is not anymore the TGT, the KRB TGT, because this is not a TGT, but it is the LDAP server, which means that this is a service ticket. And so this is the name of the server. Since this is LDAP, it means that this is a TGS, so a ticket granting service, or a service ticket, however you wish to call it. Now, at this point, a lot has been mentioned. A lot of names, a lot of like tickets, different kind of tickets, principal, realm, whatever. Authentication service, ticket granting service. Now we will see in action all these components in the flow of messages, which ultimately it is the most important point. So let us now analyze in detail the messages in a typical Kerberos authentication flow. Now the flow is described in the following sequence diagram. It's going to be in the resource of the video. So these are the high level most important messages that you must understand. We have the client, we have the authentication server, we have the ticket granting server, and we have the specific service we are trying to access. Now those two components form the KDC. So this is the centralized point of trust in a Kerberos context. So everything, I'm going to give you a high level overview of what happens, and then I'm going to go into details over each single message. So the first message that is sent is the AS-REQ between the client and the authentication server IS. And in this message, the clients want to say, look, I want to enter within the Kerberos realm, within the Kerberos context, give me a TGT. Now, where does the first authentication happens? Well, this actually depends on how you configure your AD instance. What do I mean by that? There are two places in which authentication can happen within the protocol. Either in the first message, and authentication is checked by the AS, or in the TGS-REQ message, which is the second request message, and the authentication is done by the TGS. However, if you do the second way, if you do authentication here through the TGS, you are actually vulnerable to an attack called AS-REP roasting. And why do you think it's called AS-REP roasting? Because in this attack, the idea is that in the first message, I do not authenticate myself. the AS, the authentication servers, will give me the AS-REP message. This contains a bunch of things, including the TGT and other stuff, other data. I can use this entire message to crack the user password offline. So this is the problem of doing authentication later on. So to fix this, they changed the protocol, and now within the AS-REQ message, the client has to prove its own identity. And how do you prove identity in the first message? Well, the idea is to encrypt a timestamp. You encrypt a timestamp with the client key. The authentication server will be able to decrypt that timestamp and check it with respect to the current timestamp, and if the window of time is not too big, then it will consider authentication successful. So basically that's the idea. This is also why sometimes your attacks on Kerberos will fail if your clock, the clock on your machine, is not properly synchronized with the clock of the KDC. So this is why, because the timestamp is actually used within the authentication process of the protocol. So that's basically the idea. Now let's assume that authentication happens first. So AS-REQ, the authentication server authenticates the client and then generates a TGT with a bunch of other data that is put into the AS-REP message. Now at this point, the client does a bunch of operation, extracts the TGS session key, and sends to the ticket granting server the TGS-REQ. So the TGS-REQ contains the TGT obtained by the AS plus a bunch of other data, and the ticket granting server validates everything, and if everything matches, he generates a TGS-REP. The TGS-REP contains the service ticket, and then the client uses the service ticket to prepare the APP request, which is the request to actually access the service, and if mutual authentication is required, the service will reply with an APP-REP containing another proof of authentication. So in this case, it means that mutual authentication means the service will authenticate the client, but the client can also authenticate the service. This is called mutual authentication. The first side of authentication, that is service authenticating client, is always there. The second side, that is client authenticating service, is optional. But if you put a flag into the TGS, into the service ticket, if you put a flag in there and you say, I want mutual authentication, the service is going to reply with this APP-REP, which contains another encrypted timestamp. So to prove identity, you just send encrypted timestamps to people who can decrypt that value and check with respect to the current timestamp. So basically that's the idea. So let's go through these various requests and responses. So here I have 3 AS-REQ, TGS-REQ, and AP-REQ. So this is the first request response that is sent. The purpose of this exchange is to obtain a ticket granting ticket. The entities involved are the client and the authentication service, which is part of the KDC, and there are 2 messages, AS-REQ and AS-REP. Authentication service request from the client to the AS, and AS-REP, authentication service reply to the authentication server to the client. So the AS-REQ message can contain pre-authentication data, such as PA-PAC request, so this specifies if the user wants to obtain a TGT that includes PAC data, which stands for Privileged Attribute Certificate, and it contains authorization information like group memberships and user privileges. Of course, this data can then be used by the TGS or by the service to do to perform access control, essentially. Then we have the PA-ENC timestamp. So this is contains a timestamp encrypted with the user's key. It is used to prove that the request came from the legitimate user, and it is also used to prevent replay attacks. So you cannot send the same authentication message twice later in the future, because the time window will have shifted, and therefore this is a protection against replay attacks. And replay attacks are simple attacks in which an attacker captures an entire package that is correctly formed and simply sends this to the server. But if the window of time is increased, this no longer works. So when the KDC/AS receives the timestamp, it uses the user's secret key to decrypt the timestamp, and if the timestamp is within an acceptable window of time, authentication proceeds, otherwise it fails. Now, during this authentication, different errors can happen, such as this one, error pre-out required. So this means that the client must include proper authentication data. This is to avoid AS-REP roasting attacks that we will discuss later on. For example, this other, AS-REQ, and this has to do with skew on the time synchronization. So since Kerberos relies on synchronized clock for security, significant time differences between entities can result in a time skew error. And then we find a pre-auth fail when the timestamp is not properly encrypted because the user has typed in the wrong password, essentially. Now let's see an example of an AS-REQ package. And here I've captured an authentication attempt within the Active Directory testbed. So like this testbed, I just spin up the domain controller with the KDC and the Windows 10 workstation that I showed how to set up in the first video of the series. I recorded the interface in which both of these machines use, the network interface, and then I just logged in into the machine. And this was a small packet trace of this authentication attempt. And as we can see here, we have a bunch of KRB5 messages. So these are Kerberos 5. Then here I have this distributed computing environment remote procedure called, and then here I have LDAP, and here I have also SMB2. Now, as we can see here, it starts with an AS-REQ. So this is the AS-REQ, the first request that the client makes to the KDC. So in the PA data, which is the pre-authenticated data, we only see the PAC request. So we don't see any authentication timestamp and stuff like that. And then we have the body. So we have a simple example. So this is the options. I want this ticket to be renewable, to be forwardable, to canonicalize and stuff like that. So these are the options on how the TGT should be generated. Then we find the CNAME. So this is the essentially the name of the user and also the name of the realm. Then we find the client name and the server name, CNAME, SNAME, and then we find the realm. So for CNAME, the name is Leo. For server name, the name, of course, is KerbeTGT, because this is like a TGT ticket. And then we find unknowns and a bunch of the expiry time and a bunch of other encryption types supported. And we find that the host address quick ammo, so the domain name of the machine that is requesting this ticket, essentially. So this is basically an AS-REQ. However, if we notice the trace, to this request, the server replies with an error. And the error is, look, pre-auth required. I need actual authentication because I did not put it in the first one. So in the second AS-REQ request, notice that I include also an encrypted timestamp, so this PA-ENC timestamp, which before it was not here. I mean, look at this PA data here. Now it's 2 items. Before it was only 1. Before it was only the PA PAC request. Now there is the PA PAC request, but there's also the encrypted timestamp. And here, this data, so like look at these bytes. These bytes is the timestamp that is encrypted with the client secret key. So this is proof of authentication. What the KDC will do at this point is take this blob of encrypted data, decrypt it, it will become a timestamp, and then it can check if the timestamp is alright with the KDC clock. If it is, then we're good. But of course, this does not seem the case because the next error we get is AS-REQ. So there's there is an error with respect to the timestamp. We send it again, and this time the response is good. We have an AS-REP response. So we are good with the first. So we are good with this. And this is an example of an AS-REQ with the timestamp, with the PA PAC request, with the request body, and things of the sort. So basically, that's the idea. So this is the request, and then we find the response. Now, the response contains the TGT and an encrypted part. So look at this. Go Wireshark, we have the AS-REP. We go AS-REP, we have some pre-authenticated data, whatever, we don't care about this. And we have the C-realm, as always. We have the client name. We have the ticket. So this is the TGT. And notice that this ticket, which is the TGT, has some version numbers, some things that we can read, like the server name, but it's mostly made up of an encrypted part, this ENC part, this encrypted blob. Now this TGT is encrypted with the KDC secret key. So only the KDC will be able to read this TGT. However, there is another encrypted part, this ENC part, which is encrypted with the user key. so with the user secret key. And this is the idea, is that the user will read this encrypted part and will get a bunch of different data. So that's basically the idea. So the encrypted part, which contains the session key and other authentication details, such as the TGS name, the timestamp, and the lifetime of the TGS. So the most important thing that this encrypted part contains is the TGS session key. So TGS session key. And the idea is that the client will receive this encrypted part, so this ENC part, will decrypt it, and the most important thing that it will find in the decrypted part is the TGS session key, which the client is going to use in the next message, in the TGS-REQ message. So at this point, we have AS-REQ to authenticate the client, AS-REP, not AS-RESP, AS-REP, to obtain the TGT and to obtain the TGS session key, which is different from the TGS secret key. So consider this. The TGS secret key is the long-term secret that knows the KDC of KDC. The TGS session key is only established for the current session with respect to from the client to the Kerberos to the KDC. So this is the first request and response. So at this point, we can analyze the second request response that is sent. So the purpose of this other exchange is for a client to obtain a service ticket ST using the previously obtained ticket granting ticket and TGS session key. Now this interaction happens with the ticket granting service, the TGS. So the entities involved are the client and the TGS component of the KDC. There are two messages: ticket granting service request and ticket granting service reply. So the TGS request contains the TGT that was generated by the authentication service in the first exchange. And remember, the client cannot see this data. For him, it's just a blob of encrypted data. Then we find the service principal name, the SPN of the requested service, and the desired lifetime for the service ticket, because after all, the objective of this request is to obtain a service ticket. And so here we specify which service we are interested in. And finally, we have authenticator data. And this authenticator data is used so that the TGS, before generating the service tickets, knows that we are the proper client. So this includes the timestamp and the encrypted, the user ID and the timestamp, and these are encrypted with the TGS session key. So remember that the TGS session key was obtained in the response, in the authentication service response here. There was an encrypted part which was encrypted with the user key, but this could be decrypted by the client, and within this encrypted part we find the TGS session key. So at this point the client knows this session key, and the TGS, the ticket granting service part of the KDC, uses this key, uses this authenticator data to authenticate the request from the client. So if this data matches the one that is written in the TGT, then we have a valid request. And here we can see an example of a TGS request package. So yeah, TGS request, the version of the Kerberos, version 5, the type of message, the pre-authenticated data. So we find the TGS-REQ here. We find the TGT, the ticket, and the authenticator. And then here we find the service principal name of the service you're trying to connect. For example, LDAP dc01exam.lab. And the nonce, like other stuff that is less important. And if you go into Wireshark here, we can see that essentially in this thing we have TGS request, so here, and we have this AP-REQ, so we have the ticket, the authenticator, which is of course is encrypted, and we have here the request body with the service principal name, S name, with, in this case it's an host, so in this case it's an host principal. So basically that's the idea. So at this point, we can analyze the point of view of the TGS to prepare for the TGS reply. So once the TGS receives the message, so now at this point, the KDC has to generate the service ticket, right? Which is responsibility of the ticket granting service component of the KDC. So once the TGS receives the message, it performs the following operations. It decrypts the TGT with the TGS secret, so with the KDC long secret. It reads the TGS session key from the TGT. it decrypts the authenticator data with the TGS session key, it validates the authenticator data with the TGT data, because now he has both data and he can just check if they are equal to make sure that the user did not change his identity. His identity is also written in the TGT and the user cannot write the TGT, cannot modify the TGT. If everything goes well, the TGS prepares the service ticket and it encrypts it, so this is important, it encrypts it with the service secret key. And also it encrypts some other data with the TGS session key. And what it encrypts is the service ID and the service session key. So everything that is encrypted by the TGS session key, the user can read. Everything that is encrypted with the service secret key, the user cannot read. So we have this service ticket. So this is an example of a TGS reply packet. We have, as always, TGS reply, the Kerberos version, the message type, the realm, whatever, and then we have the service ticket. So this ticket is the service ticket. It contains the service principal name and the encrypted part, which is encrypted with the service secret key. And then it contains another encrypted part, which is this service ID and service session key. And this other encrypted part is encrypted with the TGS session key. So it means that this other encrypted part can be read by the user, while this other is encrypted with the service secret key and cannot be read by the user. However, it can be cracked, so you can use a service ticket to crack the service password. This is another attack called Kerberosting, and we will see it in a different video. So at this point we have the TGT, we have used the TGT to obtain the TGS or the service ticket, you can also call it service ticket. So this is the third request and response that is sent. The purpose of this exchange is for a client to establish an authenticated session using the previously obtained ticket granting service. So the TGS or service ticket, I mean you can call them however you want, with a specific service of course. So in this time the entities involved are the client and the service. This is the final request and response. So we have an authentication request and we have an authentication reply. So let's start by analyzing the APP request, so the authentication request. So the AP-REQ contains the service ticket that was obtained by the TGS, which was encrypted with the service key. So once again, the user cannot see this ticket, so see the similarity. In the TGS request, the user sent the TGT, which he couldn't see because it was encrypted by the KDC secret key. Now it's sending the service ticket, which he cannot see because it is encrypted with the service key. And then an authenticator. And the authenticator is encrypted with the service session key, and it contains data that the service can use to authenticate the client. And so this is an example of an AP-REQ package. So we have the version of Kerberos, here we have a ticket. So this is the service ticket and this is the authenticator. So this is the request AP-REQ, and then we see the reply. So when the service receives the AP-REQ, it performs the following actions. It decrypts the service ticket in order to obtain the service session key. It uses the service session key to decrypt the authenticator, and it validates the authenticator data. Once everything is fine, if the authentication was successful, client and server at this point have a shared service session key. So they have a shared key that they can use in the current session. Now, the reply to the AP-REQ package can contain an encrypted timestamp, and this is used to implement mutual authentication. So, an example of an AP-REQ is the following one. EncPart, this is the encrypted timestamp. And if we go into Wireshark here, essentially we see that, okay, we have the TGS-REQ. Here we have a bunch of requests. So this one is for the service principal name host, while this other is for the service principal name LDAP. So this is the most interesting one. Then we have a TGS-REP. So this contains the service ticket and the encrypted part for the user, which contains the service session key. So the user decrypts this stuff and obtains the session key. And to finish up, we find the LDAP bind request, which contains, if we go into the LDAP message here, so bind request, authentication, we have this, we have a bunch of other stuff, and then we have the Kerberos blob. Now in the Kerberos blob here we see the AP-REQ. So the AP-REQ is, look at this is sent by the client. It contains the service ticket for the LDAP service principal name with the, of course, encrypted part of the service ticket and the authenticator data. So the service decrypts the ticket, decrypts the authenticator, checks the validity of the authenticator, and then is able to establish an authenticated session. For example, in this case, this is the bind response. So in this response, within internal stuff, we find the Kerberos blob, the AP-REP, and the AP-REP, it just contains the encrypted timestamp to perform mutual authentication. And with mutual authentication, we refer to the two sides of authentication. The first side is the service authenticates the client. This is on by default, and this happens within the AP-REQ request, so the AP-REQ message as we saw. The second side instead happens in the reply of the authentication request, essentially, only if the flag mutual require was set in the request. So it means, if we go here into the request, this bind request, this is the request we do to the actual service into Kerberos, AP-REQ, here we see AP option, and we see mutual required true. When we put this true, we want the service to produce this encrypted timestamp. The timestamp will be encrypted using the service session key, and so the client can decrypt it. And so these are all the messages. It is useful at this point to do a big overview recap over everything we said, and I prepare everything that matters in this Kerberos flows.txt, which will be available in the resource material in the GitHub repository. So let's start from the top. The first request is sent from the client to the KDC AS, and it is used to provide the identity of the client. So in this request, we find if Kerberos is well configured, so not always, but in the good configuration of Kerberos, we find the timestamp encrypted with the client key. This is used by the KDC to prove the client identity, to do the first authentication. In the reply of the authentication request, we find the TGT, which is encrypted with the KDC key, which means that the client cannot access this data. But we also find the TGS session key, which is encrypted with the client key. So the client will access this data, will access the session key. So this is the first flow. Then we find the second flow. So here maybe I can just separate them like this to be a little bit more clear. So now the client talks to the KDC, but to a different component. It's not the AS anymore, but it is the TGS. And it sends the TGT obtained from the KDC previously. So the client does not touch this because he cannot decrypt it, but he also sends authenticator data. And he sends this authenticator data encrypted with the TGS session key. How did he have his key? Well, because he decrypted it from the AS-REP message, because the AS-REP message contains the TGS session key encrypted with the client key. So he's able to decrypt this, and he uses this key to encrypt the authenticator data. So at this point, the KDC TGS receives the authenticator data, so it decrypts the TGT, decrypts the authenticator data because in the TGT, he will find the TGS session key. So it's going to use the TGS session key to decrypt the authenticator data. It checks if everything matches, and if everything matches, he's going to generate a service ticket encrypted with the service key. And also is going to send to the client the service session key encrypted with the TGS session key. So once again, the client cannot really decrypt the tickets themselves, but he can decrypt the other key that is sent. So in this case, it's going to be the service session key. So notice the pattern behind Kerberos. Essentially, the idea is to use keys to encrypt keys. Here we have cryptographic keys that are encrypted with cryptographic keys. So basically, that is the idea. So at this point, what can the client do? Well, the client can read the service session key. He cannot read the service ticket. So he's going to send to the service ticket and the authenticator data encrypted with the service session key. So the service, once again, what's going to do? It's going to decrypt the service ticket. It's going to read from the service ticket the service session key. It's going to decrypt the authenticator data. It's going to validate the authenticator data with the service ticket. And if everything goes well, it's going to say, okay, let's establish a session with this particular session key. So with the service session key. And finally, for performing mutual authentication, it's gonna send to the client an encrypted timestamp encrypted with the service session key. So at the end of this, client and service will share a key, and this key is gonna be the service session key. Why do they share it? Because the client receives it at this point in the fourth message here from the TGS, while the service receives it directly from the client through the service ticket. So the service ticket contains the service session key, which is also sent to the client. So with this key, they're able to communicate securely. And basically, this is the idea of Kerberos. So I hope the video was interesting. Of course, this is like a complex topic, and in future videos, we will see practical attacks to this protocol. I will put all the references, all the material I used to prepare this video down below, both in the description and in the GitHub repository. So I hope that's gonna be useful. So this is it for Kerberos. I hope it was enjoyable and interesting. If you want to support the Extant project, subscribe to this channel and share this video and this channel with like-minded people to help me grow here on YouTube. And that's it. Thank you for watching, and to the next video.